Hello everyone. My name is Kushagra Verma and today I'll be presenting on a classic problem in computer science called the sum subset problem and how it can be solved efficiently using the backtracking approach. Let's start by understanding where this problem appears in real life. First is cryptography. The subset problem is the basis of some encryption systems where finding the right subset acts as the encryption key. Next, resource allocation. Imagine trying to assign memory or bandwidth to different users while staying within limits. This is where the subset sum helps. Finally, partition problems. A special case of this problem where we try to divide a sum into two parts of equal sum. Here's the formal definition. We are given a set A of positive integers and we need to find subsets whose value add up to a specific target value D. For example, in the set S is equals to 1, 2, 5, 6, 8 with a target of 9, the solutions are 1, 2, 6 and 1, 8. There could be multiple or no solutions. Our task is to find all possible combinations that match that sum. To simplify this idea, imagine this. You're out shopping with exactly 500 rupees. You have a list of items with these prices. Now we have to choose a combination of items such that their total bill is exactly 500 rupees. That exactly what the sum subset problem asks. Given a set of numbers and a target sum, can we form that sum using any subset? For example, here the items that we go for are the green shirt, orange juice, and the diary, with the prices 250, 150, and 100, which adds up to 500. The recursive approach is to that we explore all possible subsets using recursion. At every step, we make two decisions, either include the current element or skip it. This creates a tree of choices and we go down each path. But here's the twist. Backtracking helps us prune the tree. If the current sum already exceeds the target, or even if all the remaining elements together can't help us reach the target, we stop exploring that path. We keep repeating this until we find all valid subsets or confirm that none exist. Let's find the subset of set with elements 3, 5, 6, 7, whose elements add up to 15. This slide visualizes the solution for the same. Initially, the sum is 0, which is the first node. Now, we will be making two subtrees with the left child including 3 in the sum and the right child excluding 3. Moving further down on the left, we include 5 at left and exclude 5 in the right. Further down, with 6 in the subset, the sum becomes 14, which isn't what we are looking for. Hence, this node will be pruned. Now exploring the set without 6, adding 7 to the subset in the left child gives us the sum of subset 357 equal to target 15. Now we will print this solution and backtrack and explore other combinations. This is how the whole tree can be structured. This slide shows the actual code implementation of the recursive backtracking algorithm. Here, sum of sub function solves the sum subset problem using backtracking. It recursively explores whether to include or exclude each element in the subset. The integer p keeps the track of the current sum, k is the current index in the set, and r is the remaining sum of unused elements. The function first tries including kth element of the set and marks it in the array X. If this leads to a sum equal to the target D, it prints the current subset. If the sum is still less than D, it recursively includes the next element. Then it also explores the path of excluding the kth element only if doing so still makes it possible to reach D. These decisions and checks help prune unnecessary paths, and reduce computation, which is the main idea behind backtracking. Now let's talk about performance. In the worst case, we may explore all 2 to the power n subsets, so the time complexity is big O of 2 to the power n. This can also be solved by using the recurrence relation Tn is equals to 2 into T of n minus 1 plus order of 1. This recurrence relation is built because at each step, the algorithm makes two recursive calls, one including and one excluding the current element, resulting in the 2 to the 2 into t n minus 1 term. The one accounts for the time taken to print a subset. We can solve this recurrence via substitution method, which results in the time complexity of big O of 2 to the power n. For space complexity, it's order of n because of the recursion stack and temporary storage used to build subsets. This is why we use this method only when n isn't too large or when optimization through pruning is effective. Although we focused on backtracking, there's a more optimized approach, dynamic programming. Instead of exploring all combinations, we break the subset into smaller subproblems and store the results, avoiding recomputation. We use a 2D table DP which stores whether it's possible to achieve some j using the first I elements. This brings us the time complexity down to order of n into s, where s is the target sum. So DP is better for larger inputs, although it requires more memory. That brings us to the end of this presentation. Thank you.